Hi and welcome back. Today our video is going to be looking at some non-equilibrium systems. And the dot point for today is 5.1.c. Analyse examples of non-equilibrium systems in terms of the effect on entropy and enthalpy. So before we go into what these non-equilibrium systems are, we really probably need to refresh what our enthalpy and entropy is. So let's go. So you should remember from our Year 11 Module 4 course, our entropy. And our entropy is that letter S that we've been talking about, and it's that state of disorder, moving from an ordered system to a disordered system. And it's the different ways that that energy can be distributed there. So the greater the number of different states, the more entropy that system has. Now, our entropy can be increased in a number of different ways, either one, by increasing that species, or two, the total amount of energy in there. So if we increase the temperature, we're increasing that entropy due to the increase in colliding particles. Another way is also by increasing the volume of the system. Now, just in case you've forgotten over the holidays, that formula for our change in entropy is the entropy of our products minus the entropy of our reactants. And in contrast, I suppose our enthalpy is our letter H, and it refers to the total amount of the energy that the system has. And you might often see it as a delta H, which is our change in enthalpy, because we can't actually measure the actual enthalpy of each system, but we can measure the change that occurs during the course of the reaction. So when we are actually talking about a change in entropy, we also look at those states. So remember, gases have greater entropy than liquids, and liquids have greater entropy than our solids. So if we have equal moles of on each side of the equation, but one is 6 moles of gas and one is 6 moles of solid, then the side of the reaction that has that 6 moles of gas has a greater entropy. So now we're going to look at those non-equilibrium systems, and the two that we're going to investigate are our combustion reactions and our photosynthesis reactions. This video is going to concentrate on our combustion reactions for today. Now, these combustion reactions are a little bit tricky because they're still being studied, and a lot of people still don't know completely about these reactions, but we'll give it a go. So the first one we're going to look at is our combustion reactions. Now, if you remember again from studying combustion reactions, what that is when we are burning a fuel in oxygen, and if it goes to complete combustion, we're producing carbon dioxide and water. So it doesn't really matter what fuel, if it's a hydrocarbon such as methane, which is like our natural gas, or whether it's ethanol, which is now used in many fuels, or even octane. You would have heard of high octane fuel. They are our fuels, they're hydrocarbons. React in oxygen, all of those are going to produce carbon dioxide and water as their products. Now, these ones are considered irreversible reactions. So with any of those fuels that I've just mentioned, our products are carbon dioxide and water. They will be produced in different ratios due to the balancing of equations, but those products, if they were to combine, how do I know which one of those fuels it's going to produce? I don't. And too much energy is required to go back and produce that, so it's a non-equilibrium system anyway. That reversible reaction is not possible. Let's have a look at one example here. So this is our propane, and our propane is reacting here in oxygen, and as stated before, we're producing carbon dioxide and water. So looking at this equation, let's look at the numbers here. What can we say about the entropy? So let's look. In the left-hand side of the equation, we've got 1 mole of propane and 5 moles of oxygen, so 6 moles of gas. And on the other side, I'm producing 7 moles of gas, because the water there is not in the liquid form but in the gaseous form, because there's a high amount of energy being produced there. It's high temperature, and so it's going to be water vapor. So we've got 7 moles on that side. So our entropy is leading towards that forward reaction. Then if we look at enthalpy, it's a it's a combustion reaction. Its goal is to produce a whole heap of energy. It's an exothermic reaction. So in that case, our change in enthalpy is a negative one. Now let's look at this example, and I'm going to get you to do a calculation on this one. This is our not our propane, sorry, our octane, our high octane fuel. And it again is reacting in oxygen and producing carbon dioxide and water. You'll notice the quantities are different of the carbon dioxide and water in the molar ratio, but still the products are the same. So this reaction is occurring at 100 degrees Celsius, and our delta H is negative 5,114, so that's the exothermic reaction, it's negative, and our entropy is a positive 384 joules per mole. What I'm going to get you to do is to stop the video and do this calculation and see if you can calculate Gibbs free energy. So remember, Gibbs free energy, delta G is equal to delta S minus T delta H. Now remember, temperature should be in Kelvin. You'll need to convert that 100 degrees Celsius to Kelvin. And also have a look at the units there. We've got kilojoules per mole for our delta H, and we've got joules per mole in our delta S. So go and do that calculation, pause the video, and let's see if you come up with the same value as what I have. How did you go? One thing to note before I show you the answer to this equation, and if you need me to go through it in class tomorrow on the board, I will. Looking in this reaction here, we have got our one directional arrow. So you'll notice that you're going to need to really pay close attention to these arrows now that we've introduced the concept of non-equilibrium reactions. So all those reactions you've done in the past that have gone to completion are really non-equilibrium reactions, and we need to be careful that we're using our single direction arrow for our non-equilibrium reactions, and then our double-sided arrows when we're talking about our equilibrium reactions. So if you have a look here, what we should have gotten was a Gibbs free energy of negative 5,257. So it's a negative value, saying that that reaction is spontaneous in the forward direction, and quite a big number. So it's a real push to that forward drive. We'll have a look at these a little bit further in class.